And now Peter and Ian will be presenting SeaGlass, enabling citywide IMSI-Catcher detection. Okay.
Okay, thank you for coming. Is the mic okay? Okay, great. So we do have a lot to cover in the next 15 minutes, so let's get started. I'm Ian Smith from the University of Washington Computer Security and Privacy Research Lab, and my colleague,
Peter Ney,
also from the Security Lab. We're here to present our research on SeaGlass, which is a cellular measurement system that we designed and deployed with the goal of enabling citywide cell site simulator detection. So, just quick background on cell site simulators. These are also known as IMSI-Catchers and Stingrays, and there's a lot of different makes and models of these devices, but what they have in common is they act like fake cellular base stations for the purpose of surveilling or otherwise attacking cell phones. And they do this during the cell selection and the cell reselection process. So for example, we have a cell phone here. You know, you can imagine we just powered the cell phone on. The first thing that it does is begins a cell search where it starts scanning the cellular environment for all the base stations in the area and then choosing the base station to connect to. It does this using a number of different criteria like signal strength and base station with a network and other properties that are broadcast that we'll get into later. A cell site simulator, though, might roll up in an unmarked van, like we see here, acting like a legitimate cell tower and coaxing the phone to camp on it. And in doing so, the phone reveals some private information like the IMSI, which is the unique subscriber identification number. And this, because the phone is camped on the cell site simulator, it has a number of capabilities where it can attack the cell phone. For example, it can precisely locate the phone using directional antennas, and it can perform eavesdropping attacks on phone calls, send SMS spam, and even inject malware. So many privacy implications here: location, communications, content, and possibly malware, which is, you know, game over on cell phone privacy. So not only, though, are these attacks possible, but they're also common. For example, in about half the states in the US, state and local law enforcement have cell site simulators that they use for surveillance purposes, as well as what we've learned from public records requests and anonymous leaks that 13 federal agencies use them as well for surveillance purposes. And not just law enforcement, but also criminal use. You can build these yourself for a few $100s with a laptop and a software-defined radio. And for example, in China, thousands of cell site simulators have been confiscated, sending hundreds of millions of text message spam, often containing malware links. And even though law enforcement use is controversial in the US, they've been used to hunt undocumented immigrants and solve crimes ranging to the severity of locating the robber of a stolen box of chicken. And we also know that federal marshals fly kind of military versions of these devices in airplanes over US soil that can capture thousands of subscriber information and locations at a time. And so most of what we know about cell site simulators are from anecdotes, anonymous leaks, Freedom of Information Act requests, but we know very little about who uses them, how often they're used, where they're used, and for what purpose. And so what we need is objective data on their use in the wild. And so a measurement system to be able to answer these questions using kind of technology to find objective data rather than relying on whistleblowers and FOIAs and stuff. And so in particular, goals of such a measurement system would be longitudinal, so that we can collect data over time on their use and look at kind of historical sensitive events like protests to see if they're used there. Also wide coverage, so we can monitor their use across the city. And the measurement system should be manageable so that a small group can run the system feasibly. So our solution to this is SeaGlass, which we designed and deployed for 2 months in a trial across 2 cities, 9 sensors in Seattle and 6 sensors in Milwaukee during the spring of 2016. So just let's talk about the design of SeaGlass before we get into the data that we collected and what we learned from it. Just starting at the bottom, the basic unit of the SeaGlass system is a sensor. And basically, it's a Raspberry Pi with a number of components connected to it, such as a GPS. So we always know the position of the sensor at all times. And then also a cellular modem that can scan the cellular environment, looking for all the base stations in the area and kind of collecting information on it. We chose for our deployment to use GSM, the same methodology really though applies to higher level protocols like 3G and 4G. But basically by building a sensor like this from commodity parts, they can be built relatively cheaply and they can collect much richer data than phones. So the GSM modem, for example, scans the GSM spectrum, records data like the frequencies of all the base stations in the area, their signal strengths, which we can match with the position of the sensor, and also lots of identifying properties of the base station and configuration parameters that they're broadcasting. And so we installed these sensors, kind of taking a note from war driving, installed them into volunteers' vehicles. We chose ride-sharing drivers' vehicles because as they kind of drive around the city, canvassing the city, they go to all these different areas constantly, right? 40, 60 hours a week sometimes. And so one of our other kind of goals of the sensor is to make it robust and low maintenance, so they never have to open the box or anything like that. And so we have a hotspot in the sensor so we can log in remotely and kind of upgrade and troubleshoot problems as they arise. And the hotspot also allows us to upload this data continuously to our cloud collection database, where we can learn the baseline cellular environment across the city and then perform anomaly detection with all this data to find signatures of cell site simulators. And Peter will explain more about that data and what we collected and what we learned from that.
All right. All right. So before I get into the how we use this data to collect cell site simulators, I'll give a little statistics about the system. So one thing we found that was with relatively few sensors, we were able to collect lots and lots of data. So between Seattle and Milwaukee, we had over 2.1 million cellular scans in a 2-month collection window. And we were actually able to canvass a very high percentage of both cities. So over 99% of Seattle and 95% of Milwaukee had measurements taken at least once. And in the densest parts of cities, like near downtowns, we collected over 100,000 measurements per square kilometer. Another really nice property was that our measurements quickly converged, so that within about a week of collecting data, we actually had measured over 80% of the base stations we would eventually record. So now that we have all this data, how do we actually use it to detect cell site simulators? At a high level, our approach is to learn a baseline of the cellular network with this aggregated data, and then try to find anomalies that we think are indicative of cell site simulators. And so what we're actually looking for are what we call signatures, which are basically behaviors or properties that we expect from cell site simulators, but not normal base stations. And we spent a lot of time kind of thinking about how the behaviors between the two differ and how we would actually try to identify these in the data. And so we came up with a lot of classes of these signatures. So we look for things like spoofed broadcasts, short-lived transmissions, moving transmissions, strange broadcast properties, unusual channels and location information, and information about the phone, how it would connect with phones, like whether there was encryption enabled. And I'm just going to pick a couple of these signatures and go into detail on what we found. But if you want to learn more, you should check out the paper. So all base stations broadcast information about themselves to make their presence known to nearby phones. And this includes things like what network they're part of and their identifiers, like the cell ID. And the same thing has to be true for cell site simulators. So one kind of simple idea might be to look for identifiers which have never been seen before, or which seem to be only appearing for a short period of time, because that could be suspicious. But the issue with this is that that might not actually be sufficient, because there's nothing to prevent a cell site simulator from actually spoofing the identifiers of another base station in the city. And so this is a difficult case to detect because it can actually spoof all the properties, including the frequency, so it can look very similar to the real legitimate base station that's transmitting. So to handle this case, which we kind of think is one of the harder detection cases, we decided to try to use statistical techniques to model each base station. And what we did was we used the received signal traces that we collected from all the sensors to estimate base station parameters like position, transmit power, and height that best fit the underlying data. And then once you have a model for each base station, you can use it to actually find individual measurements which appear highly anomalous and don't fit well into the model. And so to give an example of this, here is a base station, a single base station that we had measured, taken lots of measurements. This is in downtown Seattle, and this looks relatively normal. In this case, a darker color corresponds with stronger signal strength, and so you see that it's decaying like a normal base station that you would expect. But we actually found an additional measurement over 3 miles away that was fairly strong in West Seattle. And one thing that was really nice was this kind of anomaly was automatically detected by the modeling. We didn't have to individually look through thousands of base stations to kind of find these. We can sort of automatically basically model each base station and then compute a likelihood for each measurement and then filter for likelihoods that are very low. And these kinds of values pop up. However, one limitation with this modeling approach is that it might actually be possible for a cell site simulator to mimic a legitimate base station that's very close by, so its transmissions might hide within the signal of the legitimate base station. And so we wanted to run some simulations to test this case and to see how feasible this was. And we found that if the spoofing transmission was within 1 kilometer, it was very difficult to detect. But as it moved further away, we had progressively more detectability. And so at about 4 kilometers, we were able to detect around 60% of the time when this case happened with 80% true positive rate. But I note that in reality, it's going to be difficult for a cell site simulator to transmit too close to the base station it's mimicking, because if it's transmitting on the same frequencies, then it would likely interfere with it. And if it's using different frequencies, then it would stand out a lot, because all the base stations seem to very consistently transmit their broadcasts on the same channels. So another signature interested in looking at was broadcast properties. And so all base stations also transmit a number of additional properties besides identifiers, and we collect over 19 of these. And one thing we found by looking at the data was how extremely consistent these properties were within each network in the city they're operating. So unless a cell site simulator was specifically designed and configured to mimic the broadcast properties of the network it's spoofing in the city it's being used, then its values would likely stand out. And so a simple example of this is here's a broadcast property we measured in Seattle. We found that all the AT&T base stations had one value, all the T-Mobile base stations had another value. So when we found a base station that was advertising as a T-Mobile base station and it had a very anomalous value, it was very easy to notice it, and it stood out. But there are actually other reasons why cell site simulators might modify these properties, and that's because some of these might improve its ability to capture phones and minimize interference. And so these 6 values highlighted in red are suspected or known to be used by cell site simulators to kind of improve their capabilities. And so we had a really good example of this near the SeaTac airport in Seattle. And so we found that over the course of 2 months, we had been measuring the single base station, which is whose measurements are shown over there. And its values were the same all the time and inconsistent, and were very consistent with what we expect for that cell network. However, there was one time on April 9th where we actually picked up measurements that were supposedly for the space station that were completely anomalous with what we had normally seen and very out of line with what is expected for the network. And all 4 of these are properties that are suspected of being connected to cell site simulators. So in summary, cell site simulators we think they're a really important privacy problem that's a little understudied. And we think more measurement systems in particular are needed on real-world usage. Also, we found that SeaGlass style platforms are a really effective measurement collection system for all sorts of radio technologies, not just cell phones. So we think this kind of approach of using ride-sharing drivers can be really effective. And if you're interested in additional details, check out the paper where we describe some other anomalies we found, including an anomaly near a Customs and Immigration Services building. So thank you.